Hello. We will continue the discussion which we started this week, and in today's and possibly tomorrow's lecture, we will continue to review some of the mathematical concepts which are highly relevant to finite element method. So, what we are going to do is today review integration by parts, and then try to explain how this particular procedure is very helpful in context of finite element method. So, we will discuss integration by parts. So, this is the part review. So, let us assume that u, v and w. So, right now we are just talking about a one dimensional domain, and they are sufficiently differentiable. What is sufficiently differentiable? That if I need a second order derivative, it should exist. That is sufficient enough. It may not have third order derivative. If my need is only up to second order, then an x square type of function is sufficiently differentiable. But if I need second order and if my function is just x, then it is not sufficiently differentiable. So, these are all sufficiently differentiable functions of x, which is the independent variable. And suppose I want to integrate this guy w, which is a function of x times dv over dx, and I have to integrate it over the domain a to b. So, I want to integrate this thing. Now, this can be expressed as, and we will show the proof later today itself, is equal to minus v times dw. So, dx goes away. Okay. So, this is v times dw plus function w. So, w's and v's are functions, they are not constants. Strictly speaking, I should have written it like this, but for purposes of brevity, I am not writing it. So, w times v in the limits a to b. This is the final answer, and we will get the final answer. How we get it? We will review it. Proof. And this is a very important thing, at least in context of FEA. So, we know that derivative of two functions w and v equals v times derivative of first function plus w times derivative of second function, which is v. So, I get w, because I have to get this on the left side, dv over dx is equal to minus v dw over dx plus w v d over dx. Okay. So, I have just reorganized this. Now, what I do is I integrate. Okay. So, I will write it on the next line. So, now I integrate this equation over limits a to b, and this is equal to minus V dw over dx plus integral of wv So, now I continue this thing. So, this is w times dv integral of from a to b, and this equals, so this dx and dx they can cancel each other. So, I get basically a to b v dw plus again this dx and dx they cancel, and essentially when I integrate this guy I get w times v a to b. Okay. So, this equation is same as what we had written earlier. This is the same relation as this relation. So, we have shown that this equation is there. Okay. Now, this is a very important equation from standpoint of finite element method, and what it does is, and we will see its impact today itself, what it does is that here it transfers the differentiability. Here this has been differentiated v, that differentiability has been transferred to w, okay. And then of course, we have the boundary terms. So, we are transferring differentiability from v. In our case, it could be that v is the residue, v could be the residue and w could be the weight function, and through this method we are able to transfer differentiability from the residue to the weight function. Why that is important, we will see it a little later, but this is something important to note. So, this is for this function w times dv over dx. Now, we will do this one more time. Okay. So, similarly, I can have another relation. Suppose I have a fourth order differential w times d4 u over dx4 dx. Suppose I want to integrate this thing, then how do I do this? Or before that, actually let us do the second order thing. So, this is equal to minus, this is a to b, oh I am sorry, u. So, this is equal to dw over dx times du over dx times dx plus w times du over dx a to b. How did I get this? It is basically coming out directly from this thing. Here what we have done is, here this is double derivative of u. So, I can assume that v is equal to du over dx. Okay. I can assume that v is equal to du over dx. I plug this thing here. So, here I get v, it gets replaced by du over dx, w is same, and instead of v it is du over dx. Okay. Now, think about it. A lot of our equations in one dimensional, for instance, if I am trying to pull a bar in tension, it is governed by second order differential equation of this type, a du over dx and then d by dx plus u is equal to some function q, something like this. Okay. Similarly, the heat conduction equation in one dimensional is a second order differential equation. Okay. So, you will get in several equations second order derivatives. You will also get u times w. So, when I am trying to compute residue, I will get a second order derivative multiplied by w, and of course, in this case u times multiplied by w. When I do this math, what happens is that this side is equal to the right side, and here if I am computing the left side, you remember that we assume different values of phi's, right. For a linear element, it could be linear in nature or quadratic or things like that. So, here the requirement, one mathematical requirement you will see directly here is that u has to be at least of class 2. Okay. But if I transform this integral to this type, then u only has to be of class 1 thing. Okay. So, that is one thing, that my requirements of differentiability here for u have gone down by 1. This is one thing. And the second thing is, this is symmetric. No, okay, so right now I will not call it symmetric, but the requirement on w is 1, class 1, requirement on u is also class 1. Okay. Now, later in the FEA course, what you will see is that this balancing of differentiability on the weight function and this other function is related to the error. So, balancing of differentiability on weight function and the unknown variable, if it is balanced, then it leads to symmetric matrices. We will see this later. We will actually do the mathematics, we will see this later. And when we have symmetric matrices, then solving symmetric matrices is much easier than solving non-symmetric matrices. Equations which have non-symmetric matrices, it is more complicated. If matrices are symmetric, then it is faster. So, that is another thing. And then there are some more advantages of this thing. So, what we have done is, in this case, in the LHS, differentiability requirement for u was C2. We needed a C2 class of a function. If we transform this to the right side, differentiability requirement for u becomes C1. I mean, if it is C2, no problem, I mean, it will do the job. Okay. What we have done is, we have weakened differentiability requirement. We have weakened, this term it comes in a lot of finite element literature. We have weakened the requirement of differentiability. Okay. And that is why this method, once we weaken it, it is known as weak formulation. It is not that the answers are poor or something like that. The differentiability requirement has been weakened, so this is known as a weak formulation. So, this is for second order. So, you see the benefit of this for second order derivatives. Okay. Now, we will check one more thing. Consider a beam. The equation for beam is what? I will not use W, let us say U is the deflection. This is the equation for a beam, right. If U is the deflection of the beam, I is the moment of inertia. This moment of inertia can change with respect to the length of the beam. Suppose this is a beam. I am putting some force here. right? Because of this is my x axis, deflection is happening here. So, that this deflection at some point is u is deflection and u is a function of x, and q is the loading. This loading could be a point load or a distributed load. Okay. So, this is what? This is a fourth order equation. It is a fourth order equation. So, when I construct its residue, and I multiply it by some weight function, and I integrate it, let us say, between the length 0 to L, which is the domain, or if I am doing it for an element, then it will be from H1 to H2, right. It does not matter. I mean, the theory, right now the theory is I am talking about, does not matter. So, actually to make it more generic, I will say I will integrate it from A to B. What is the differentiability requirement for R in this case? It will be fourth order, fourth, right. Why? Because when I W, what is R? R is EI Cj phi j summation I is equal to 1 to n, you differentiate it 2 times, minus q dx right. This is my residue. That is the residue. So, I am basically, the relation says integral of W times EI and then summation of Cj phi j double prime prime, Cj's are constants, phi j I have to differentiate 2 times, and then from the right side I bring in Qx. So, if this is not exactly 0, then there will be a residue. So, that is why it is called residue, and then differentiate this whole expression twice and then integrate this thing with respect to x. So, this is my, and this entire thing is weighted integral of residue. This is weighted integral of residue. So, in this case, differentiability requirement on phi, or I can also call u, because phi is u is a function of phi, right, is what? Fourth order, right. So, this has to be a fourth class. Oh yes, you are right. Yeah, you are right. That is there. Okay. So, it is fourth order. Now, using this method, this integration by parts, if I integrate it once by parts, I will reduce the differentiability to 3, and if I integrate it 2 times, then I will reduce it to 2, right. So, that is what I will do, and that will conclude this lecture. So, if we integrate it by parts 2 times to balance differentiability between W and U. So, that is what we will do. So, So, suppose there is a fourth order derivative and you will apply this result directly to that beam equation if you want, and there is a, let us say in this case weight function is V, I should have written it as W, okay, and the unknown is W, okay. So, this I can express it as A to B. So, here weight function is V, W is the unknown function. So, V W prime 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 dx, and let us say that W prime prime I call it as U, okay. So, then this becomes A to B V U prime prime dx, and when I integrate it by parts I get minus A to B V prime U prime dx plus V U A to B. This is V U prime, okay. So, now it is V prime and U prime. So, between U and V it is balanced, but U is itself a double derivative. So, it is, so here on U my continuity requirement is 3 and on V it is 1. So, now I integrate it one more time. So, now what I do is A to B, so I integrate it by parts one more time, okay. So, I get minus, so again this minus, again I get another minus, so it goes away. So, I get V prime V double prime U dx minus V prime U A to B plus V U prime A to B, okay. And now what I do is I replace U by W. So, I get integral A to B V double prime W double prime dx minus V prime dW over dx A to B plus V d2 over dx square, oh actually this should be cube, A to B. So, I will write down the left side also, V okay. So, if there is a fourth order equation, then I have to integrate it 2 times to shift the differentiability and make the system balanced, so that the differentiability requirement on my weighting function and the unknown function is same. So, we have seen that how we do it on second order function and how do we do it on a fourth order differential equation. Second order could be a heat conduction equation, heat transfer, not heat conduction, heat transfer equation. Fourth order could be like a beam or elasticity problem, things like that, okay. So, this concludes our lecture for today. We will continue this discussion in context of 2D systems tomorrow. Thanks.